In this video, I just want to look at some random groups as well as some subsets and show if they are subgroups or not. The first one I want to look at, I'm going to let H be the set of all log of A, such that A is a rational number that is greater than 0, and I want to know if it's a subgroup of R under addition. We need to start with two elements of H, so we'll have log of A and log of B, assuming that both A and B are rational numbers that are greater than 0. And we need to look at their sum, since our group is under addition. Properties of logs tell me that this is log of AB. Well, since A and B are both rational, and A and B are both positive, we know that AB, the product of two rationals, is still a rational, and the product of two positives is still a positive. So it is closed under addition. What about under inverses? Since our group is under addition, we need to really look at negatives. So I need to look at negative log of A. Properties of logs tell me this is the same thing as log of A to the minus 1. Well, since log of A is in H, we know A is a rational number and it's greater than 0. The inverse of a rational number is still rational. And since taking the inverse of a rational number is just the reciprocal, signs will not change, so A is still positive. So yes, this is a subgroup. This time, the only thing that I'm changing is, this time I'm looking at log of n, where n is an integer. So this time we need something like log of n plus log of m. Once again, using properties of logs, that's log of nm. And since n and m are both positive integers, so they are both nz and positive, multiplying two integers is still an integer, and multiplying two positive numbers is still a positive number. So it is closed under addition. Since we're looking at our subgroup under addition, we need to look for negatives for inverses. So now I want log of, or negative log of n. That's log of n minus 1, but we have an issue. For instance, if I want to look at log of 2, which is perfectly fine, the negative would then be log of 1/2. And this half right here is no longer an integer, so we're no longer in H. So this does not belong to H. So this is not a subgroup. This time, let's consider the set H, which is equal to all 2n 3 to the m, where m and n are integers. And I want to know if that's a subgroup of R star under multiplication, the non-zero reals under multiplication. So I need something in the group and something else. So this time I'll use A and B instead of M and N. Properties of exponents tell me this would be 2 to the n plus A, 3 to the m plus B. Well, n and a are both integers, so n plus a is an integer. M and b are both integers, so m plus b is an integer. So that tells me that this is accurate. We are closed under the group operation. What about inverses? 2 to the n, 3 to the m, inverse. Properties of exponents tell me this is 2 to the negative n, 3 to the negative m. Well, n is an integer, and changing the sign of n, it still will be an integer. Same thing with m. The negative of an integer is still an integer. So this is a subgroup since we're closed under the operation as well as inverses. Let G and H be any groups. I'm going to consider the set of all elements of the form x comma e, where x is in G and e is the identity of H. And I want to show this is a subgroup of G cross H, the direct product. Well, we're going to take something of this form and something else of this form. So let's consider x and y and g. This would be, by definition, xy, comma, e times e would be e. And since x and y are in G, xy will be in G, since G is a group and it will contain products. Now let's consider the inverse. Well, this would be the inverse of x. The inverse of e, we know the inverse of e is just e. And since x is in G, x inverse is in G, since once again G is a group and it has to be closed under inverses. So yes, this is a subgroup.